concept, and then you propose. And then after you propose, then you can do the lab, doing experiment and so forth, and find out. But in reality, you don't have to go through really. Yes, you can go through the dry run. In industry, what we do, we make a proposal, and then we make a what we call conceptual model. Then we go to the lab and test it out. The same thing with the copy machine. The copy machine concept is how to use a photo sensor and lot smaller and desktop type. So you got to from complicate and simple, and then go down to the nitty-gritty. Now this one, Isaac Newton is basically under the tree, right? And here's Isaac Newton, and looking for the apple. The apple keeps dropping. He said, why is it so? Now, for the regular individual, oh, so weird, that's normal. But he questioned. Now, this is what makes the scientific invention come through. Called curiosity and find out why. So a lot of this kind of scientists is like a nerd, keep looking at it. The other people is thinking he's a madman or something like that. But he's actually dreaming why it dropped. So finally he says, if this is a drop, and then he says, if this is a dropping, so you visualize, here is the Earth. And then here is center of the Earth, and the things is just dropping, and then toward the center. And then he says there must be a force there, so force in it. So he's making assumption. The force between these two mass, in this case is a mass m, assuming this is a mass m1. And the whole thing here, if we're assuming, make another assumption, means that the Earth, the mass of the Earth is concentrated at one point, in which case usually we call the center of mass. And this whole mass concentrated here is M2. So there's a gravitational force among between them. So in which case it's F sub g is proportionally to M1, M2 divided by the separation of R, in which case it's R squared. So for some reason, somebody giving a hint, it's R squared. How come not R cubed? Sometimes, how come it's not R? So this is takes a what we call major assumption. And when you develop this concept, is back in this Newton's gravitational. The Newton proposed this in year 1666. This is approximate. So he just lived there. He can't do anything. He just proposed this. He didn't do any measurement. So if you ask me, I think the other gentleman doing more work than Isaac Newton. So in 1798, so almost 125 years later. 125 years later. Now, it takes about that much gap. So you could question, how do other people? This is a gentleman, is called Cavendish. Cavendish do the actual experiment, in which case he's using a very, very primitive equipment to do it. He built a giant wood ball. It's very giant than those woods. and then real tiny mass, and then hanging down with the what we call the galvanometer. Galvanometer is a very sensitive device, and then he try to find the proportionality constant. With this concept, you cannot apply anywhere. You cannot, based on this, approximately send the satellite to the moon. You cannot build a rocket and then doing a lot of propulsion. This G equal to M1, M2, R squared. And then with very careful experiment, and they demonstrated in your page 338 how to using galvanometer and combination, and you find out G. Remember, this is comparatively speaking, this was discovered about 102 years ago, 202 years ago. We find out G is equal to 6.673 times 10 to minus 11 Newton and Newton meter square and kilogram square. He found out this unit. Okay, this one. So they make the Newton, the gravitation law complete. Gravitation law complete. So is G equal to G times M1, M2 divided by R squared. G is equal to 6.673 times 10 to minus 11 Newton meter square kilogram square. 10 to minus 11 is very, 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 very tiny number. Now, nature has its own is a simplicity. This is based on M1, M2, and then separated by R. And then later on, on the physics 31B, we will start the charge of electrical force, in which case it's called Coulomb's force. Coulomb's force. Now, Coulomb force is there's a force among them we call F sub E, in which case is equal to K times Q1, Q2 divided by R squared. Again, it's a similarity between them. One is related with mass, another one related with charge. But the electrical force are much, much larger than F sub G. So consequently, the F sub E, the electrical charge, is very easy to be detected. Because F sub E is approximately equal to 10 to the 40 F sub G. Now, the electrical force are much, much larger than the gravity force. So, doing the lab, doing the research, finding out electron, finding out proton, finding out neutron are a lot easier than graviton. So we 15 years now, the program is looking for graviton. So far, we are not getting yet. Okay, the government invested a lot of money to looking for graviton. The laboratory is down at the Caltech and down at the, what we call the Australia, Hawaii. Somebody told me that they might have a station in Alaska for looking for those. So this is the gravitation law is finally get into concrete. from this on, we can do a lot of application. For example, the application-wise is related to building up what we call the structure atom. Structure atom in relationship with the electrical force among the charges. If you take the orbital motion, the locus or orbits, they turn out to be electrical. And then we say, how can we get out of the Earth for us? For example, how to escape from the Earth attraction. Basically, we've done all those for section to 11.4. So we move on to the section 11.2. 11.2 section turned out to be the structure atom. Structure of atom. All this have a base on a lot of study. There's a two person is our very famous person is give us a lot of headache for developing the structure atoms. Structure atom, Plato is against it. Plato and Aristotle, they are against the atomic theory. These two gentlemen strongly oppose the atomic theory or the structure of atoms. Structure of atom. Takes about studying is called John Dayton. John Dayton is a chemistry teacher, high school teacher, and he using the atomic theory to explaining a lot of chemical reaction. So he done a very good job on this. What John